moving back and forth from a history graph to a snapshot graph, or a snapshot graph to a history graph is not, it's not trivial. It's not something I expect you come in knowing. With reason, we can get through this in a fairly straightforward set of steps. But a lot of times there's the push. Oh, I should recognize this. I should just do this, la, 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 la. And problems arise and pain occurs. This is actually very common in physics. I suppose there are a number of cases where you look cooler or you look more impressive if you can solve a problem in the class by simply just sitting and reasoning through it. By looking, oh, I shall look cool, think about it and have an answer. In physics, that is exactly the wrong thing to do. It's why, in the case of force problems, in face-to-face classes, there are free body diagrams. And we will use those again when we get back into force problems in just a couple of chapters. But in a face-to-face class, if you go through and work a force problem and don't use a free body diagram and skip steps, I will not even grade it. Skipping steps just brings pain. It doesn't make you look good. It just makes you look foolish. Now, let's take a sample of a snapshot graph. Oh, let's say that at a given instant, here is my snapshot graph. Now, obviously I don't have, ooh, that'd be cool, like a gridded whiteboard. That'd be awesome, actually. We don't have that, darn. So, suppose this is at 2 meters. For this, for clarity's sake, I'm going to assume number's good to 3 significant figures. Why? Because too few and it's easy to lose material in the way that we're going. Now, so let's say this is 2 meters. Oh, let's call that 5 x in. Oh, let's say centimeters. There is 10 centimeters. $12 centimeters, 14 centimeters, 17 centimeters. So, and we have a wave that's moving in the plus x direction at a speed of 2 centimeters per second. Now, suppose I want to make a history graph for a particular point. Actually, I'm going to say, let's make a history graph. Okay, this is a snapshot at t equals 0 seconds. If I look at this history graph of x is equal to 10 centimeters, what do we have? Well, at this instant, well, let's see, I need to make random guesses. Let's say that's plus 3. This is in centimeters as well. And call that minus 2. So at t equals 0, the instant this was taken, the value of x is at, the displacement, y, is at 3 centimeters. Now, constructing that, let's look at what was happening. Okay, so if this is moving in this direction, then what's going to happen is that in 1 second, this will be 2 centimeters over. So in 1 second, this point will be at x is equal to 12. In 2 seconds, it will have moved 4 centimeters. And in 2.5 seconds, it will have moved 5 centimeters. So, 4 this displacement will be at y is equal to 3. Starting at that point, 4, 2.5 centimeters. Now, as that happens, okay, here, this drops to 0 over the space of 3 centimeters. Which means that this 0 point has to move 3 centimeters over once this point has reached 10 centimeters. This wave has to move 3 more centimeters for the 0 point to hit x is equal to 10 centimeters. So, 3 centimeters at 2 centimeters a second means another 1.5 seconds. And after that point, the wave has gone through. It's at that value forever. Now, let's look in the past. Okay? Here it is at t equals 0. So at t equals, say, -1, this whole wave is 2 centimeters farther to the left. So 1 second previously was 2 centimeters over. So at this point at which it's crossing the y is equal to 0 would be at point 10. Two more centimeters, or 1 more second into the past. It's at its bottom. It stayed at that point for 1.5 centimeters. So let's look at the shape. Let's see if the shape makes sense. What's happening is this wave was over here, comes in, and starts interacting with point 10. So initially, this is the leading wave. This is the first thing that's going to happen is it's going to get knocked down to -2. Hey, the first thing that happened 3.5 seconds in the past is this got knocked down to -2. It'll stay at -2 for at least some period of time, then rise up to 0 and then up to -3. Positive 3. It'll stay at positive 3 some function of time until it drops back down to 0, and then the wave has passed through. Notice that this is the case for a wave moving to the right, moving toward positive x. Suppose I've got a situation where this was moving the velocity was 1 centimeter per second to the left. Well, if I wanted to make a history graph out of that, okay, at this starting point, t equals 0, I'm still up at my maximum value of 3. But now, if the wave is moving in the opposite direction, well, that means that okay, what's the next thing that happens? This is all going to move 1 centimeter to the left. Then after 2 seconds, another centimeter to the left. What was at x equals 12 is now at x equals 10. So in 2 seconds, that drops down to 0. After another 2 seconds, it hits its negative value. This is still moving in this direction. It has to go 3 centimeters, so it has to take 3 seconds. And then the wave is through and gone. So that's for positive time. What happened before I took my snapshot? Before I took my snapshot, it was sitting up at this level for, this length of this wave is 5 centimeters. So at 1 centimeter per second, that's 5 seconds of sitting up there. And then it drops down. It had, let's see, it was moving in this direction. So this part hit the wave first. So at some time it started moving upward. And it took 3 centimeters, and at 1 centimeter per second, 3 seconds to reach the value. So, if I'm going from a snapshot to a history graph like so, here's what's, if this happened to be moving at a speed of 2 centimeters per second to the right, here's the history graph that I'd get. If this were moving at a speed of 1 centimeter per second to the left, there's a history graph that I would get. This is going from a snapshot to a history graph. Working from a history graph to a snapshot is much the same. Let me know if you would like to see a specific example of that as well.